Hi everyone, bonjour. The IB Crocodile is here. Welcome to my YouTube channel specialized in providing supporting academic videos for both math and physics. Today, I'm going to present all about partial fractions decomposition. This is a subtopic in advanced algebra. There are 5 types or cases for partial fractions: linear factors, repeated linear factors, quadratic factors, repeated quadratic factors, and improper fractions. So pick your pencils and let's have fun. I'm going to start with a layout or common layouts of partial fractions decomposition as per this table here. And the main idea of partial fractions that you have a certain function or certain rational function, right? And then you need to decompose or break it down into a simpler fractions. Okay, this is the opposite operation of combining two fractions. So when you combine two fractions, for example, you would find the common denominator, right? But then partial fractions decomposition is the opposite operation. So there are some layouts. So it depends on the layout. You know, you're gonna choose your starting point or your starting form, right? It depends on the original rational function. Okay, so this table here is just for reference. I'm going to break down all of these cases into 5 cases. So let's move on and start with the first case. So case 1, linear factors. So what does it mean? When you look here at this, for example, 3x minus 3 divided by x minus 4 times x plus 2. So first of all, you know, x minus 4, this is called a factor. And it is linear. Why it is linear? Because it is first degree. So you always ask yourself, okay, what is the degree of the factor that we are having or that we are seeing in the rational function, right? So x minus 4 is first degree because degree is the highest power of x. So x minus 4 is linear, and also x plus 2 is linear because again x to the power of 1 here. So the layout or the form of this rational function is going to be, you started with, let's say, a constant a divided by x minus 4, okay, plus a constant b divided by x plus 2. Okay, now here is the important remark that the constant or the numerator has to be lower by 1 degree of the factor. Again, the numerator or the b or the constant has to be 1 degree lower than the denominator. In other words, you see x minus 4 here is linear as we agreed, right? And it's a first degree. So that's why I chose a as a constant, which is basically 0 degree. Okay? Again, x plus 2 is first degree, linear. So the constant or the numerator has to be of 0 degree, as if you multiplied b multiplied by x to the power of 0, you know, so that's 1 degree lower than the degree of the numerator. Now, if you imagine, you know, if you would like to combine these two fractions, right, you would actually choose the common denominator, that x minus 4 times x plus 2. So that is step 1. Okay, look at the layout and decide the form, you know, that is according to the layout of the original function. So that is step 1. Now step 2, so now anything power 0 is 1, right? So I just here b basically, right? Now step 2, this is what I would do. I would multiply both sides by multiplying both sides by the original denominator. Okay, so for example here, okay, we have 3x minus 3 divided by x minus 4 times x plus 2. I'm going to multiply this side by x minus 4 times x plus 2. So you multiply both sides by this whole denominator. Okay, and that is equal to now a over x minus 4 plus b over x plus 2, and that is also multiplied by x minus 4 times x plus 2. Okay, so let's see what will happen. So obviously we can cancel x minus 4, x plus 2 from the left hand side. So then you will have here on the left hand side 3x minus 3. And then we're gonna like expand, right? So a multiplied by x minus 4. So this guy here, right, will cancel with that factor there. So you will left with a multiplied by x plus 2. Okay, so we have a multiplied by x plus 2, and then b multiplied by, again, x plus 2 will cancel there, right? As if you like expand, as you just, multiply inside the brackets. So x plus 2 is canceling here, and then b is left with x minus 4 being multiplied. Okay, so that step is very important. You multiply both sides by the original denominator. So then, the next step, comparison of coefficients. Comparison of coefficients to find a and b. So our target here, of course, is to find a and b, right? So, or the constants. So we can expand. So we can say, okay, so a times x is ax, and then a times 2 is 2a, and then bx, and then negative 4b, right? And then we have on the left hand side 3x minus 3. So now we can compare the coefficients. Now, what is the coefficients of x on the left hand side? This is the coefficient here, is basically 3. Now the coefficient of x on the right hand side, if you take x common factor here, you will end up with a plus b, right? I mean, if you take x common factor between these two terms, right? So you will end up with a plus b, which means a plus b is the coefficient, right? So that implies what? That implies a plus b is equal to 3, right? Just comparing coefficients. So a plus b, the coefficient of x on the right hand side, is equal to the coefficient of x on the left hand side. The same way we can compare the absolute value or the constants, right? So we've got here 2a minus 4b. So 2a minus 4b, these are constants, and they are equivalent to negative 3, which is the constant on the other side. So then you end up with two equations and two unknowns. You can easily solve them by elimination, or if you have a graphic calculator, you can just plug the coefficients in the GDC, and you get a and b if it is paper 2. So what I would do here, we can get rid of a if you like. So let's multiply this equation by 2. So this is equation 1, and this is equation 2. So I'm going to multiply equation 1 by 2, or if you want by negative 2, if you like, so you can just add right away. Okay, so let me multiply it by negative 2. Okay, so negative 2 times a is negative 2a, and then negative 2b, right? And 3 times negative 2 is negative 6. So then you can add them. When you add the 2a, it cancels out. Negative 4 minus negative 4 negative 2 is negative 6. So negative 6b is negative 9, right? You can just cancel the negatives, right? So b here, b is going to be 9 over 6, or basically 3 over 2. So that is the first constant, b equal 3 over 2. And then you can substitute in any of the equations. Let's substitute in equation 1. Substitute in equation 1. So what you have here, so a plus, and now instead of b, we have 3 over 2 equals to 3. Right? And then we need a by itself. So what you would do, you can move 3 over 2 on the other side with negative sign. So it's going to be 3 minus 3 over 2. I mean, 3 over 2 is basically 1.5. So 3 minus 1.5 is also 1.5. So you get a right away 3 over 2 as well, right? Makes sense? There's 3 plus 3, 6 over 2 is 3. So that is A and B. Okay. So then what the final, or the basically now the final answer for this, or the final like layout, decomposition, maybe I can just go back to this original form here. So I can just replace A by its value. So this original function here is going to be A, which is 3 over 2, and then you have x minus 4 down, and then plus b, which is 3 over 2 as well, multiplied by x plus 2. Okay, so that is the way of doing or decompose a rational function. That is case 1. Let's now move on to case 2, which is repeated linear factors. Repeated linear factors. Let's see what is the difference between now this function and the previous one. First of all, it is still linear. So still linear means what? Means still have x to the power of 1, which is the highest power of x, which is the degree. So now x minus 1, again, the factor is linear. But when you see to the power of 2 or to a certain power, that means it is repeated. Okay? So the way to deal with that, is going to be, anyway, we're going to have A as a constant because it is linear. So A over x minus 1, right? But then plus B over x minus 1 all to the power of 2. And that is called the repeated linear factors. So the constants up are still following the rule, which they are 1 degree lower than the factor. Okay? But why I have to add now two of them? Because if you look here at these two fractions here and ask yourself, what would be the common denominator between x minus 1 and x minus 1 to the power of 2? So the common denominator here would be x minus 1 to the power of 2, right? So that is my original function. Okay, so that's why we have to put the possibilities. We have to put the possibilities. One fraction could be over x minus 1, and the other fraction, could be over x minus 1 to the power of 2. And then work if one of the constants is 0, it's fine. But this is the general form that you need to follow. Okay, so then I'm going to do the same thing. So I'm going to multiply both sides by x minus 1. Okay, so I'm going to multiply both sides by x minus 1 to the power of 2. I will just write it here. So multiplying, both sides by the original denominator. So x minus 1 to the power of 2, the one on the left-hand side. Okay, so now if you do that, right, so 2x plus 1, 2x plus 1 over x minus 1 to the power of 2 multiplied by x minus 1 to the power of 2. And then that is equal to A over x minus 1. Okay, you can even distribute right away. So that is multiplied by x minus 1 to the power of 2. And then plus B over x minus 1 to the power of 2 multiplied by x minus 1 to the power of 2. And then what you can do here, you can cancel this, the top from the bottom, right? So on the left-hand side, you end up with 2x plus 1. Now I can cancel this only with the square. So I'm left with A multiplied by x minus 1. And then here, B is standalone because we can cancel both brackets from top and bottom. So then again, step 3, expand and compare the coefficients. So it's going to be here ax minus a plus b, right? So then you compare what is the coefficient of x on the left-hand side is 2. What is the coefficient of x on the right-hand side is a. So right away, we can say that implies a is 2. That's it. So we got a. And then we can compare now the constants with the constants, right? So that implies that 1 is equal to negative a plus b, right? But then now we found A actually as 2. So we can say 1 is minus 2 plus B, or negative 2 plus B. So then what is B? B has to be 3. So that implies that B has to be 3, right? I mean, you can just move negative 2 to the other side. So negative 2, I mean, plus 2. So plus 2 plus 1, it's 3. Okay? So the final answer, or the final decomposition here, so this f of x here is going to be 2, A is 2, right? Divided by x minus 1, and then B is 3 over x minus 1 all to the power of 2. Okay? So if you look again at this final answer, and if you think, okay, what would be the common denominator of these two fractions? Obviously, common denominator. So it's going to be the LCM, or x minus 1 to the power of 2, which is this guy here. Okay, so far we covered linear factors and repeated linear factors. Now, case 3, quadratic factors. So quadratic factors meaning what? Meaning second degree. Meaning what? Meaning the highest power of x is 2. So here in this example here, we started to see quadratic, x squared plus 1. Okay, so now remember, okay, the layout or the rule. So if you now want to introduce a numerator, or break it down now into like couple or 3, whatever, small fractions or simpler fractions. Okay, so if you say, okay, I need something over x squared plus 1, right? Now x squared plus 1 is quadratic. So the numerator has to be 1 degree less. So that's why we need to put ax plus b. So I have to put just a linear, right, to the power of 1 to be 1 degree less than the denominator. And then the second factor here is basically linear, because we have x minus 1 only. So we can just put any letter, you know, just a constant, which is 0 degree. Okay, so this is the first step, is the most important step. Okay, to recognize what kind of factors we have, and then you put your layout, you put your form, right, according to the original function. Now you tell me what is the next step. You may pause the video if you like and go ahead and solve this, and then come back to me after, and then you double check. So what you're gonna do, so the next step is to multiply both sides by the denominator. So here is going to be 2x minus 1. So I'm going to multiply by the whole thing here, right? And then that is equal to ax plus b, right? If you multiply, it was over x squared plus 1. So if you multiply by this denominator, so this x squared plus 1 will cancel with that factor here. So you will left only with x plus 1, x minus 1. So here is going to be x minus 1, and then plus c multiplied by, so x minus 1 again will cancel if you multiply, and then you will end up with x squared plus 1. Okay, so then we can expand. Okay, I like direct method. I mean, there is FOIL method, but it's not my favorite. So I like direct method. So you multiply each term by all terms in the other, on the other bracket, and once you finish, you move to the second term. This is called the direct method. So ax times ax is basically ax squared, and then ax times minus 1, so negative ax, plus bx. Now I can move to the second term, so bx and then minus b, and here we have just cx squared plus c, right? Now we have 2x minus 1. Okay, so now let's compare the coefficients. Okay, what is the coefficient of, let's say, x squared on the left hand side? So on the left hand side, do you see any x squared? The answer is no. So that means what? That means the coefficient of x squared is 0. So 0 on the left hand side. Now on the right hand side, okay, let's see what are the terms in x squared. So we've got here ax squared plus cx squared. If you take x squared common factor between these two terms, you know, you end up with a plus c, obviously, right? Which means 0 is equal to a plus c, and then we can call this equation 1. Now let's look at the coefficient of x on the left-hand side, which is 2, right? I mean 2x, coefficient of x. And then let's see on the right-hand side. So we've got here negative a plus b, right? That's it. So that's it. So 2 is equal to, let's say, b minus a. It's up to you. So b minus a or negative a plus b. Okay, so still we have, okay, we need one more equation because now we have 3 variables, right? So then the constant or the absolute term, so it is negative 1 on the left-hand side, and it is on the right-hand side, it is basically c minus b. C minus b. Makes sense? Because c minus b is the constant, right? I mean, represent, there is no x. So this is absolute term, and that is basically equal to negative 1 by comparing coefficients. And this is equation 3. Now we have 3 equations and 3 unknowns. We can do them by substitution. Okay. So let's see what we can do here. Okay, from equation 1, what we can say, here from equation 1, that a is equal to negative c. You can just bring c to the other side with negative sign. Okay, and then if you plug in a here with c, so then you will have 2 equations in b and c only. So I think that's a good approach. So we can do that. So let's substitute here in equation 2 by a is negative c. So this becomes 2 equal b minus, and then instead of a, I'm going to put negative c. So minus minus plus. So 2c, so 2 equal b plus c. Right? And then we have here negative b, equation 3, plus c is equal to negative 1. If you add those equations, so b cancels out. So you'll have 2c here, and 2 minus 1 is 1. So that implies that c is 1 over 2, right? So once you get one variable, now just a domino effect, we can just plug in, now we've got a right away because a is negative c, right? So that means a also is negative 1/2 because we have c already, right? Now we can apply in any of the equations to get b, right? It's up to you, whatever. So let's substitute in equation 2. So substitute in equation 2. So 2 is b, which we don't know, right? Minus a, which is negative 1/2, right? So minus minus, again, negative times negative is positive. So b plus 1/2 is 2. So what is b? 1.5, right? So that means or implies that b is 1.5 or 3 over 2. So we've got now our variables or unknowns. So now I can substitute back in the main form, right? And we can say, okay, so this main fraction or main function, rational function, it can be equivalent to, now a is negative 1/2. Okay, so it's going to be negative 1/2 x, and then plus b, which is 3 over 2, and then that is over x squared plus 1, and then c is basically 1 over 2 multiplied by x minus 1. Okay, of course you can take 2 out, and then you can just bring it down here. So it's going to be negative x plus 3 over 2 times x squared plus 1. Okay. So what is this case? This case is just quadratic factors, right? Which means the factor itself is second degree, and that's why the numerator has to be first degree in the form of ax plus b, or whatever the letters you can choose in the letters, doesn't matter. So now this is case 4, repeated quadratic factors. We just covered case 3, which is quadratic factors, basically second degree, right? But then this is now repeated quadratic factors. So the general form is negative 4x or certain rational function with negative 4x plus 1 over x squared plus 9 all to the power of 2. So if you look at the denominator here, we still have a quadratic which is x squared plus 9. But because it is to the power of 2, so that means it is repeated. So in this case, I need to set up my form as ax plus b, so 1 first degree, which is less than second degree, right? So x squared plus 9, right? Plus, let's say cx plus d, right? Over x squared plus 9 all to the power of 2. Okay, so now we cover the two options of the two possibilities. You say, okay, if I take the LCM or the common denominator between these two denominators, you will end up with the original denominator of the rational function. So now my target or our target now is to find all these constants. So as you know, we multiply both sides by the denominator of the original function. So if you multiply by that, you will end up on the left-hand side, negative 4x plus 1. Now, ax plus b is going to be multiplied by x squared plus 9 because it's already over x squared plus 9, right? So one of the square here, one of the brackets will cancel with that guy here, and then plus cx plus d multiplied by 1, or basically, yeah, because it's already over the whole denominator, so it will be canceled out if you multiply by the whole denominator both sides. Okay, now let's comparison of coefficients. Let's expand a little bit. So here, let's a direct method. So ax cube plus 9ax, and then bx squared plus 9b plus cx plus d. I just did very simple direct expansion, expansion of the brackets using direct method. And we have on the other side negative 4x plus 1. So let us investigate the coefficients. So let's say coefficients of x cube. Do you see any x cube on the left-hand side? The answer is no. So that means the coefficient of x cube is going to be 0 on the left-hand side. But then we have ax cube. This is the only term with x cube here that implies a has to be 0 right away. So we know a is 0. Now let's have a look at the coefficient of x squared. In the same manner, there is no x squared on the left-hand side. So the coefficient is 0. But then let us see what are the terms with x squared. I mean, I see here only bx squared, right? So that implies b is 0. That means a is 0 and b is 0. Okay, now let's examine coefficient of x. So it's negative 4x on the left-hand side. So minus 4 or negative 4 on the left-hand side. And then if you look at the right-hand side, let me pick another color here. So we look at the right-hand side. Let us look at the terms where x. So you have 9ax. Oh, and we have also we have cx. Okay, if you take x a common factor between these two terms, you end up with 9a plus c, right? So that means the coefficient of x on the right-hand side is 9a plus c. But since we got a is equal to 0 anyway, so this term is gone. That implies c has to be negative 4. And then the absolute value is positive 1, or you can just write 1, right? So you can just write 1 on the left-hand side, which is equivalent to 9b plus d, right? 9b plus d. These are the absolute values or the absolute terms on the right-hand side. But then we got actually b equals 0 from a previous step. So this guy is gone. So that implies d is equal to 1. Okay, so we found that even this term, we assumed it is there in the beginning. This is the right way. But now in this case, for example, we found that A and B are zeros. So this term was not there in this particular problem in partial fractions decomposition. Okay, so we end up with, okay, you can put back C and D in there with their values that you found, right? So negative 4x plus 1 over x squared plus 9 all to the power of 2 has to equal to basically the same thing. C is negative 4 and D is 1. So basically this is the this is the maximum, or this is the simplest form on any way of that fraction. Okay, but this is how you deal with repeated quadratic factors. So you set up your form. The numerator is first degree because it has to be 1 degree less than the denominator, and then you have to consider the two cases. The first case with the bracket and the second case with the factor to the power of 2. Okay, next one, case 5, improper fractions. So what do we mean by improper fractions? The improper fractions where the degree of the numerator is higher than the degree of the denominator. In this case, you cannot do partial fractions composition. Okay, so partial fraction composition or decomposition, only applies if the degree of the numerator is less or equal the degree of the denominator. In this case, the only way here is long division. So we need to do long division, right? And see where we can go from there. Okay, so what I would do, say, okay, so we have 3x cubed minus 6x squared plus x minus 2. So, okay, divided by x squared plus 3x plus 2. So what you do in the long division, you divide the first term by the first term. So 3x cubed divided by x squared, so which is 3x, right? And then you multiply it back, right? So 3x times x squared is 3x cubed. And then we have plus 9x squared plus 6x. And then change the signs. Please don't forget to change the signs. So here of the bottom line. So here is going to be negative, this is negative, and this is negative. So 3x cubed minus 3x cubed cancels out. And then we have minus 6 minus 9 minus 15 x squared. And then you have 1 minus 6, which is negative 5x. And then minus 2, I can just, bring it down here. Then the next step, the same process, you divide the first term by the first term. So negative 15x squared by x squared, negative 15, right? So minus 15 here. And then you multiply back. So minus 15x squared. And then minus 15 times 3x, which is negative 45x, and then minus 30. And then what you do, that's right, you change the signs. Okay, so you have here positive. Now this guy becomes positive, and this sign also becomes positive. And then you see, you just do algebraic addition here. So minus 15 plus 15 cancels out. And then minus 5 plus 45. So that is 40x. And then minus 2 plus 30, right? So 30 minus 2 is 28. So basically plus 28. Make sense? Okay. So now this guy here, we call it the remainder. Okay, which is the remainder over whatever we divided by. And this guy here, we call it the divisor. So this is the divisor. Okay. And this is basically the quotient or the result of the long division. Okay. So now how we can write now, how now we can rewrite the improper fraction that we started with, you know, so we write the quotient, which is 3x minus 15 plus the remainder 40x plus 28 over the divisor, right? The quotient, you know, by itself plus whatever remainder still divided, you still have remainder here. So remainder over x squared plus 3x plus 2. Okay. By the way, this 3x minus 15, the quotient is called the oblique asymptote. So as a matter of fact, if we have, this is a case of improper fractions or, you know, improper rational functions. So if the degree of the denominator is higher than the degree of the denominator, there is no horizontal asymptotes. No horizontal asymptotes in that case, right? So therefore, when you do the long division, you know what you get from here, you get this straight line here, 3x minus 15 is a straight line, you know, is with the slope 3 and y-intercept negative 15. So that is basically the oblique or slanted, we call it oblique, you know, slanted or oblique asymptote, right? So this is the oblique, we call it oblique asymptote. So this is just a side note, but it's important, you know, I got to mention it here. So that is, yeah, oblique asymptote. And again, in this case, if the degree of the numerator is bigger than the degree of the denominator. Asymptote. Now, if you want to continue simplifying these partial fractions, okay, let us see. Now we have, you know, 40x plus 28 over x squared plus 3x plus 2. Now you may actually factor this. Let's see. If I say x plus 1 multiplied by x plus 2, right? So 1 times 2 is 2. 1x plus 2x is 3x. Just factoring. And you can tell what is this case. That's right. This is linear factors, right? So this guy here can be even simplified as certain constant over x plus 1 plus another constant over x plus 2. And you back to case number 1, linear factors, and follow the steps and find a and b and finish your partial fractions decomposition. Okay, so these are the 5 cases. This is all about partial fractions decomposition, all what you need to know in your program as an IB student, mathematics higher level. And yeah, and these are basically, yeah, the 5 cases. I hope it was helpful. Thanks for watching. Please feel free to leave any comments, likes, and have a nice day.